So how much resolution do we really need for a given measurement requirement? And the way that you go through the analysis of this will be shown here. For instrumentation measurements, we have the sensor resolution. Typical sensor, maybe 0.5%, 1 part in 200. So if we only measure that with 8 bits, which has an equivalent to 1 part in 256, that's we're going to lose information by digitizing. I mean, we're going to lose too much. So typically we'll say, let's look at 10 times the sensor resolution or effective accuracy, which would be 1 part in 2,000. And a 12-bit A to D converter has a resolution of 1 part in 4,096. And in fact, 12-bit A to D converters are very popular and have been very popular for a long time for industrial and instrumentation measurements. Much finer resolution than the accuracy of the device. And it allows us to look at small changes. In many cases, instrumentation now has gone more to 16 bits. It gives us even finer resolution and fits the standard computer word of 16 bits. But you can do this same analysis yourself according to the type of sensor that you have. Dynamic signal measurements, if we take the audio as an example, what we would like would be to have 0.1% distortion at 5% of full scale, or where the music, say, is at somewhat low level, and most microphones, speakers would be pretty hard pressed to get down to 0.1%. So that's equivalent to 1 part in 20,000. Go to 16 bits, and that's 1 part in 65,000. So this is the analysis that they went through in the 80s when they were trying to figure out how to set the resolution for the original CDs. And in fact, it's 16 bits. Some music, particularly as cared for by purists, is available at 20 bits. Very fine symphonic recordings and the like. You'd actually like to be able to have a little better dynamic range and better noise performance at low levels, so they might push it out to 20 bits. But standard music is at 16 bits, and if you're looking at really loud rock and roll, I don't think it makes a lot of difference. But that's how you come to that analysis. Now, if we look at the errors, we'll talk a lot about the LSB in this discussion, and you'll see that often in data sheets and the like, and that's the least significant bit. And we saw that with the 4-bit data converter, the difference between the two, a jump is 625 millivolts. That's the value of the LSB, or the least significant bit, the smallest change, and it's often given as percent of full scale. The offset would be where the first code changes. It might not be at half of an LSB. The gain is then what the slope is. Nonlinearities would be then changes in the actual slope. And we'll take a look at some of these. And these are data converters that don't work very well in these charts. In this D-to-A converter, we find that from code 011 to 100, the output actually goes down, and this is known as non-monotonic behavior. This gives you pretty bad distortion for dynamic signals, and is often bad for feedback control systems, because you send a signal to have it go up and it actually goes down. It really messes up the signal, causes it to hunt. For an A to D converter, we see that the code 100 is never represented. We jump directly from 011 to 101, and this is known as a missing code in the output of the A to D converter. And data converters are often rated in terms of at what level of performance or conditions, they start to show missing codes like this. Again, that's a distortion. We also have noise levels where, in fact, from code to code, the transition might not be at exactly the same point that we showed on the original curve, or the original design or the layout of the part, where it doesn't exactly fit at halfway between the codes. It's particularly for high-speed ones, that transition might happen at different points. That introduces more noise to the effective performance of the data converter. So there's several specs that we won't go through in a lot of detail right now, but particularly for dynamic systems, signal-to-noise ratio, and distortion are all important. Spurious-free dynamic range has to do with very high-frequency parts. So then we also have quantization and quantization noise. Quantization is another word to describe digitizing or converting an analog to digital signal. So quantizing means that we're converting it to a code. And at the bottom, we see that if we measure the effective output of the data converter against the straight line analog input, we get an error function. And that can be described mathematically. And this is the minimum amount of noise, and this is just from the effect of quantizing the signal. Additional noise from poor performance will also be added to this. And if you go through the math, we find that the effective error of this, or the noise, is equal to Q, which is the value of the least significant bit, divided by the square root of 12. And we won't do that math today. But again, this is the minimum error that you would experience. Okay, so that we just discussed then the errors in the y-axis, or the how accurately we can measure